Good afternoon, calculus. Let's just get this out of the way. There's a bunch of people testing in here. Say hi, ladies. Hi. Hi. Okay. That's just because it's going to be weird anyways. Me over here talking to myself. That's all right. Today we're going to be learning about the disc or the washer method. Now, for those of you who don't know what a washer is, I'm not talking about the machine. I'm talking about one of those donut-looking things. They usually go between two parts of metal. They look like that, pretty much. So a washer, right? You have a hole in the center of something, but we'll get to that in just a second. Let's go through, and I've written my volume of a disk formula over here. Pi times the integral of x1 to x2, r squared dx. Nothing new there. Let's go through and just crank out a few questions real quick, and when we get to something interesting, we'll stop and talk about it. So the region bounded by y equals 0, x-axis, y equals 4 minus x squared over 2. Now this is a parabola that's pretty wide, upside down and shifted up 4. So let me graph this real quick. Like this. And that thing will intersect the x-axis. If you plug in a y equals 0 for 4, that'll be what, the square root of 8. So a little bit more than 2. X equals 2 and negative 2, so 1, 2. And negative 2. And the rotating around the x-axis. So here's the area that we're wanting to rotate, right? And it's around the x-axis. So this is going to be relatively simple. It's just a disk question. Volume of a disk is pi times the integral, and we're going from the left bound to the right bound because we are rotating with respect to x. So negative 2 to 2. 4 minus x squared over 2 squared, there's your radius, squared, dx. Now, I do want to spend a little bit of time talking about this radius here because this is going to make a big difference to us today. Your radius, we said this before, is the outside line minus the inside line, right? So it's 4 minus x squared over 2 minus your lower line here, which is 0. So that just ends you up at 4 minus x squared over 2. So that's where the idea of our radius comes from, and we can use a calculator here and just figure this out. This is 144.094. I've already done this ahead of time. This idea of the radius we're going to start using a lot more, especially right here. I'm going to start harping on this quite a bit. Example 2 says the region bounded by the curve y equals 2. Y equals 2. 1, 2. Well, here's y equals 2. Y equals 0, so the x-axis, x equals 2. And negative 2. So I want the area bounded between all of this. So I'm looking at this little, looks like a rectangle right now, but it's going to be a cylinder once I rotate it. Rotating around x. So I'm with respect to x here. So my radius is my outer, remember this is your radius right here, outer minus the inner. 2 minus 0, which is just 2. So I have pi, the integral from negative 2 to 2 of 2 squared dx, and that is 50.265. So again, the part that I really want to harp on for a little while is this piece right here. We have a couple of examples here where this radius is going to end up changing. And going to get a little weird here. On example 3, it says the region bounded by y equals 2 y equals 4 minus x squared over 2. Now this is the one from up top, so I already know what this is. Shifted up 4. Pretty wide parabola here. And the line y equals 2. Now this one's a little bit different. Y equals 2. Goodness, if I could draw a straight line, it'd save my life. And then it's revolved around the x-axis. Now that's a pretty cool key here, because this is my region. I'm going to shade this in very lightly. This is my region here. And I'm trying to revolve around the x-axis. Well, if you revolve this around the x-axis, that's going to leave a hole straight through the middle of your revolution. So we've got two things that we've got to take into account here. We've got the volume is going to be the volume of your disk minus the volume of your hole. For a second, let's just pretend like everything was filled in, right? And it went all the way down here even. Well, then it'd be pretty easy to see. You rotate it around X and it's just the volume of your disk. But now, I'm taking out this center piece. So I've got this hole straight through the middle of it. So let's see if we can come up with something here. We've got the disk is pi times the integral. And let's call this the distance from the x-axis to here. Let's call all of this r squared, big R, or big radius. And then the distance from here to here, little radius. Your delta x is still the same here. This is your delta x. So I've got the big radius, dx, minus the volume, minus pi, good grief, if I could write this correctly, pi integral little r squared dx. So take out the middle piece. And that condenses to pi, both of them have pi in common, the integral of r squared minus r squared dx. And this is the washer method. That right there is your washer method. Alright, so you basically just subtract out the middle piece, and we call it a washer because it starts to look like washers. And if you remember from today, I actually still have this here. Technically, a CD is a washer because it's got a hole in the middle of it, right? Technically, this is a washer. This is what we would be doing if we were trying to line up pieces out of this thing, and we'd have a hole in the middle of them. So let's set it up here. It's pretty easy to set up. We've got the volume. This is the washer method. Is going to be pi times the integral of the outer radius, which is 4 minus x squared over 2 squared minus the inside radius. Now this one's just 2. This is your inside radius right here. So just 2. And again, already doing this one ahead of time, 93.829. Not too shabby. So it's a pretty easy concept, and really there's one thing you need to remember on it, and I'm going to put a star at the top of the next page. If there's a hole, use a washer. If there's a hole, no, I'm talking about a hole in the middle. If there's a hole in the middle, like if it's hollowed out, then use the washer method. Example number 4. Find the volume of the region bounded by the curves y equals x and y equals x squared, and all these three are the same. Y equals x is this guy, and y equals x squared is the parabola between the lines y equals x and y equals x squared. So on every single one of them, This area right here is what you're looking for. Let me zoom in on this one so you can get a better idea of it. Here's y equals x. Here's y equals x squared. This area right here, I'll draw it a little bit bigger on the rest of them, but that's the area that I'm looking for. All right. Now, the first one says revolved about the x-axis. Okay, so on this one, the hardest part of this is going to be identifying your r's. Your big radius is going to be the same way you found your other radius. So the big radius goes from here to the top. So it's going to be x. Your small radius is going to be x squared. Right? The big one is the top. It's the distance from the x-axis to here. So technically it's x minus 0. And the bottom one is the distance from the x-axis to x squared. So again, minus 0. Alright, so your volume, this is using the washer method obviously, is going to be pi times the integral. And where do these meet? Where do these two meet? Well, this point right here is 1 comma 1. So I'm integrating from 0 to 1. I've got x squared, this is capital R, minus x squared squared. That's little r. So volume using my washer method here is 0.419. And I wish I could rotate these. I'll try and come up with some pictures to show y'all about the rotations on these. Same graph here. I'm going to draw it a little bit bigger so it will you can see it a little bit better. Here's x squared, here's x, 1 comma 1, all shaded in, revolved around the y-axis. So this is with respect to y. Good stuff. So big R is the distance from the y-axis to your outside area. That's this guy right here. This is big R. So big R is going to be, let's see, we're with respect to y. So first let's get this y equals x squared. We learned this lesson yesterday. X is the square root of y, plus and minus, but that really doesn't make a difference to us here. We'll worry about that later. So it's the square root of y minus 0, which is the square root of y. And little r, we have y equals x, so it's just y, right? Y minus 0, which is y. So my volume of my washer is going to be pi. And again, they meet at 0, 1, so from 0 to 1, these are your y values now, from 0 to 1 of big R, square root of y squared, minus little r, y squared, dy, which is approximately 0.524. So it's not too shabby of a concept. And then we get to this guy. Alright, let me draw him again. Here's y equals x, here's y equals x squared. Just drawing it to the best of my ability. All this area is what I need. And I'm revolving around the line y equals 2. Now that's actually pretty interesting because y equals 2 is up here. This is where coming up with r is going to be extremely important. So I'm revolving around this line. So I'm going to say capital R is the distance from this 2 minus to the outside x squared. Now since this is a horizontal line, it's with respect to x obviously, just like the x-axis. So there's my capital R. My little r is the distance from 2 to this inside line, which is x. So I have the volume of my washer is pi times the integral. And these, again, they meet at 0 and 1. So from 0 to 1 of 2 minus x squared, capital R, minus little r, 2 minus x squared dx. And let me enter this one in for you, just so you can kind of see it here. There it is. Let me show you how to enter this in one more time here. Clear all that out. F9. Integral from 0 to 1. Oops, I forgot my pi. 0 to 1 of all of this stuff. 2 minus x squared minus 2 minus x squared dx. 1.676. Just to give you a little idea of how to enter that in with a calculator. Yippee-ki-yay. All kinds of good stuff on the washer method. So there's a disc or a washer. If it's got a hole, it's a washer. If not, it's a disc. If it's a solid, that's all there is to it.